In this video, I'm going to show you how to derive the Bethe-Heitler formula for Bremsstrahlung from quantum electrodynamics in full detail. Every step is given and explained. The idea is that once you've watched this video, you'll know how to do the derivation completely yourself with as close to zero residual questions about it as possible. So let's get into the math section. The Bethe-Heitler formula is a differential scattering cross-section describing Bremsstrahlung in a nuclear electric field at the tree level in quantum electrodynamics. Its derivation is slightly more advanced than other differential scattering cross-sections that I have derived on my channel in past videos. There are links in the description to a few of those videos. Because it is somewhat more advanced, it isn't usually derived in quantum field theory classes, but it is usually derived in quantum field theory textbooks, and it is an important, famous, and beautiful result. It is therefore worth working through the Bethe-Heitler formula derivation, and that's what I'm going to do in this video. At the tree level, we have two Feynman diagrams, which is normal for tree-level quantum electrodynamic scattering cross-sections. In these diagrams, the dot, that right there and that right there, represents the coulombic nucleus whose electric field supplies a virtual photon for the scattering. The photon from the Coulomb field must be virtual because it is an internal line in this interaction, i.e. it does not originate from the initial state. This is where we run into problems that make this calculation more difficult than more usual scattering calculations. First, it isn't clear what the Feynman rule for a virtual photon produced by a Coulomb field is. Second, because there isn't two particles in the initial state, it is clear that the usual differential scattering cross-section general formula won't work as a starting point. Also, because there are only three particles total in the external states, we expect some novelties with energy and momentum conservation, because normally with three-particle scattering, these two things are not simultaneously consistent with the relativistic energy-momentum relation. Previously, in videos on deriving differential scattering cross-sections, I began with the usual Feynman rules and the general differential scattering cross-section formula, and then proceeded through the normal procedure. I simply referred you to videos where I had shown how to derive these prerequisites, it being necessary to do this because deriving those prerequisites is extremely time-consuming. Because those standard results are inadequate here, we will have to go back to more fundamental principles and derive the needed results from them. Instead of using Feynman's rules, we will compute the relevant part of the expanded S matrix directly, and based on our knowledge of what a differential scattering cross-section is physically, we will write out what its formula must be for this problem. Despite needing to work from more fundamental principles, the changes we need to make aren't massive. This means that I can reference derivations and calculations in those past videos whose results aren't directly applicable, to cut down on the amount of math and explanation that needs to be done in this video as much as possible. The three videos whose results can't be used directly, but whose content I will reference repeatedly, are these three: the differential scattering cross-sections in quantum field theory video, the decay rates in quantum field theory video, and the how to derive the Feynman rules for quantum electrodynamics video. I placed links to these videos in the description. Because I make important references to the contents of these videos in this derivation, it is important that you are familiar with the concepts they contain. In this section, the process of deriving the Fineman amplitude from more fundamental principles will be done, namely by looking at terms in the expansion of the S matrix. As we saw in the derivation of the usual Feynman rules in my video on that, one normally considers free, non-virtual photons supplied by the initial state, whose reaction with the electron is controlled, meaning mathematically described, by a free quantum field of this form, where, as we saw in that derivation, A plus mu of x annihilates a photon at x, and A lambda of k annihilates a photon of momentum k. In Bremsstrahlung, as described by the Bethe-Heitler formula, instead of scattering off of a real photon supplied by the initial state, one considers the scattering of the same electron off of an external classical Coulomb field. So we're replacing the situation of a photon in the initial state, whose reaction with the electron during the scattering is controlled by this quantum field, to a situation where the electron is scattering off of this field instead. So one removes the photon from the initial state and makes this replacement. One can think of this as the scattering of an electron off of a virtual photon, meaning it is not supplied by the initial state, whose reaction with the electron is given by the Coulomb field. Because the photon is not supplied by the initial state and its reaction is controlled by the Coulomb field, the virtual photon is said to be supplied by the Coulomb field. So basically Bremsstrahlung is the same as Compton scattering, but where the incoming photon isn't a normal photon coming from the initial state, it is instead a coulombic virtual photon. Therefore, this calculation calls for us to take the transition amplitude for tree-level Compton scattering, remove the photon from the initial state, and then make the above described electromagnetic field substitution. Once this is done, one can proceed through the normal derivation of the Fineman amplitude and arrive at the Feynman amplitude for tree-level coulombic Bremsstrahlung, which is what is needed for the Bethe-Heitler formula. To save time, I have just pulled the tree-level Compton scattering transition amplitude from my deriving the Feynman rules for QED video and perform the described modifications. Doing that yields this result. We can write this without the normal ordering signs as long as the operators are already properly normal ordered, which leaves us with this. Let's begin our evaluation with the A term. We can start by doing a little rearranging, which leaves us with this. With the preliminary rearranging done, we can make these substitutions. These three identities right here, if you want to know where they come from, you can watch my video on deriving the Feynman rules for QED, that one I keep mentioning. And then, of course, this is just the Fourier transform of the Coulomb potential that I gave above. Inserting those gets us to here, and then rearranging some factors gets us to this. There are no operators left, only C numbers, and we will take the vacuum state to be normalized, so then that just gives a factor of 1, leaving us right here. We can make further simplifications and also switch to Feynman slash notation. Also remember that we are dealing with transverse polarized photons, so the polarization index can be placed up or down, which allows us to write it like this. Now we can write the propagator in terms of its Fourier transform. So I've inserted the Fourier transform there and then moved some factors around and combined the exponentials, that sort of thing, and that got me to there. At this point, all the x dependents for both x1 and x2 are in these exponentials here, which allows us to do the x1 and x2 integrations to yield delta functions, which gets us down to there. Canceling some factors of 2 pi gets us to here. Now we can use this delta function identity to rewrite those products of delta functions like this, which gets us to this. Now that only one delta function depends on b, we can do the b integration to arrive at this result here. Then we can do the 3 mechanical momentum q integrations, leaving us with this and this momentum conservation relation. Now remember this, and remember that q integration there, because that'll be important later on when I discuss momentum and energy conservation in a little bit more detail in this problem. Now we can do the q naught integration, which ultimately just leaves us with this. So finally we have this result for the A term in the Feynman amplitude, and an extremely similar calculation yields this result for the B term in the Feynman amplitude. We can therefore write out the whole transition amplitude, and then this is the corresponding Feynman amplitude for tree-level coulombic Bremsstrahlung, which is what we need for deriving the Bethe-Heitler formula. From this Feynman amplitude, we can see what we would have had to select for the Coulomb virtual photon Feynman rule had we wanted to do this calculation using the Feynman rules. Specifically, we must compare the Feynman amplitude in the box with the Feynman diagrams given in the introduction. Doing this, we find that for this reaction, the complete set of Feynman rules is just these. So the usual ones, except for the incoming virtual photon, which is given by this Fourier transformed Coulomb field. With this Feynman rule amplitude question answered, we are now free to notice something else about the transition amplitude, namely the novelty with the momentum conservation that I was talking about earlier. In normal two-particle scattering, the transition amplitude would include 3 more delta function factors that are there to impose mechanical momentum conservation. We would have 3 more delta function factors here. While the usual energy conservation delta function is present, the mechanical momentum ones are not. If one analyzes the derivation of the more typical Feynman rules via the technique of expanding the S matrix and pays close attention to the delta functions, then one will notice that these energy momentum conservation delta functions specifically enforce conservation between particles that appear in the external states. We know that energy and momentum cannot be conserved simultaneously for 3 particle processes if the relativistic energy-momentum relation is to hold. It is therefore sensible that we would be missing the usual momentum conservation delta functions, because something had to give. Because mechanical momentum conservation across the 3 particles present in the external states is not conserved, there is no issue with the delta function that enforces energy conservation across them. Momentum is still conserved, however, if one includes the momentum contribution of the coulombic virtual photon, which doesn't appear in an external state. Earlier in the calculation, the delta function that enforces this alternative version of momentum conservation does appear, as you saw, and it gets integrated over at an earlier stage in the calculation, enforcing this alternative momentum conservation in the process due to the integral from the Fourier transform of the Coulomb field. Momentum conservation delta functions therefore aren't left over at the end. Remember when I told you to pay attention to that momentum conservation relation because I was going to talk about it later? Well, that's what this discussion was. Moving on, we can actually simplify this Fineman amplitude a fair amount before we continue. So we can start by factoring. That gets us from here to here, and then we can multiply and divide these fractions by factors that cause the denominators to be differences of squares, so we get to here. The first thing we can do in order to simplify these denominators there down is to prove this identity, which is easy to do from the Clifford algebra satisfied by the gamma matrices, and that allows us to write some of the terms that we get when we multiply out this square there as dot products, and then we can remember what those dot products have to equal just from the properties of four momentum vectors, and that gets us ultimately to here. Then we can rewrite this like that, and then use the Clifford algebra satisfied by the gamma matrices again to get to here, and ultimately to this dot product result there. So it's quite a simplification. We started out with this and we got all the way down to there. Of course, in this I'm glossing over some trivial details associated with dividing by matrices. Just remember that dividing by a matrix is multiplying by its matrix inverse. A similar analysis gives us this result for the other denominator. We can insert that in and we get to this result for the Feynman amplitude. Later we will need to take the modulus squared of the Feynman amplitude, so it is useful to write out the complex conjugate now. This can be done with the usual identity for calculating complex conjugates of products of matrices like this, and we find this result. You can look at my other differential scattering cross-section derivation videos for further demonstrations of that identity. With the Feynman amplitude worked out, we now need to find the differential scattering cross-section formula into which we must insert the Feynman amplitude to arrive at the Bethe-Heitler formula. This is the subject of the next section. As described in the introduction, we must work out the formula for the differential scattering cross-section from first principles because the usual expression won't work. So let's get going with that. In my differential scattering cross-section video and my decay rate video, we used a formalism where the incoming particles have a bell curve distribution in position and momentum space. A function phi of k was used to describe this momentum space distribution. However, in the derivation of the standard Feynman rules and in the above mathematics, we used a formalism where the incoming particles were plane waves. The two formalisms coincide when this function goes from a bell curve to a delta function. It fixes the average momentum k bar to be the exact momentum, i.e. the limit of plane wave incoming particles that therefore have specific momenta. In the case of the differential scattering cross-section formula derivation and the decay rate derivation, all traces that constitute a difference between the two formalisms cancel out anyway, meaning all dependence on this fi function cancels, as you may remember from those derivations. Taking the limit therefore doesn't do anything to those results. The same cancellation happens here. We are therefore free to switch to the wave packet formalism for this section for the sake of the math, and then take our result to apply in the plane wave formalism. If we still had leftover dependence on this fi function, then taking that limit would actually change something, so the results wouldn't be equally applicable to both cases without changing anything. Looking back at the calculations, particularly in the decay rate video, because that video treats a case where there is one particle in the initial state, and the transition amplitude above, we can see that the wave packet formalism version of the Bremsstrahlung transition amplitude modulus squared is this expression, where the Feynman amplitude is the same as it was in the last section. In terms of the transition amplitude, we can write the momentum space transition probability density. We learned how to do this in both my differential scattering cross-sections in QFT video and my decay rates in QFT video. Specifically, we have this result for the momentum space transition probability density, which tells us that the transition rate per unit volume is just this expression here for Bremsstrahlung. In my differential scattering cross-section derivation video, we learned that the differential scattering cross-section is merely the differential transition rate per unit volume, per incident particle, and per target particle, which in the absence of an observable target particle, meaning one that is in the initial state, this becomes the differential transition rate per unit volume per incident particle only, which is of course just the differential transition rate per unit volume divided by the incident flux, meaning we have this. In both my differential scattering cross-sections in QFT video and my decay rates in QFT video, we learned how to calculate the relevant flux. Following that process, the result that we get is as follows. The only difference is that the incoming flux is fermionic in this case instead of bosonic, and the standard normalization of states is a bit different. We can then plug the flux and the previously obtained result for the differential transition rate per unit volume into the differential scattering cross-section formula, this formula, and when we do that we get this. This is the basic result for general Bremsstrahlung, but for specifically the Bethe-Heitler formula description of Bremsstrahlung, there are a few extra details that need to be added. First, the electron and photon spins are of no interest, so the initial electron spin is averaged over and the final electron spin is summed over, as is the photon polarization. Inserting this gets us to here. Second, the Bethe-Heitler formula is the differential scattering cross-section with respect to the solid angles of the outgoing particles and with respect to the energy of the outgoing photon. This means that we need to express the momentum differentials in spherical coordinates, getting us here, and it also means that we need to integrate over the outgoing electron momentum magnitude. The delta function allows this to be done easily, but there is a little complication. We must re-express the delta function to get it into a form that is easy to integrate. Specifically, the integral we need to perform is this, and using normal identities we can rewrite that delta function like this, where f prime of pf vector magnitude is the derivative of the f function and pf vector magnitude naught is the root of the f function, or the actual value of pf vector magnitude, meaning the one that satisfies energy conservation. Because that's what this original delta function is imposing, because of the delta function the integration simply forces this assignment. We can then relabel the actual momentum with the symbol previously just used for the integration variable to make the notation simpler now that the integral is done. Specifically, the integral gives this result, where that f prime function works out to be this. And we can insert that and get this result finally for the differential scattering cross-section in terms of the Fineman amplitude for the Bethe-Heitler formula derivation, with the Feynman amplitude computed in the section after the introduction and the differential scattering cross-section worked out in terms of the Feynman amplitude. In this section, we can see that the next step is to compute the unpolarized Feynman amplitude modulus squared. This is done in the next section. Our task is now to compute the Feynman amplitude modulus squared. Luckily, in the section on the Feynman amplitude, we computed both the Feynman amplitude and its complex conjugate, so we can simply write out the needed square right here, which is just that. Now it's a scalar, so we can take a trace of it without changing anything, but then take advantage of the cyclic property of the trace to move this spinor factor there to a more useful position at the end there, which is the result we have here, and then we can eliminate the spinors entirely by performing the spin sums using this identity, which gets us this nice result, which looks easier to handle. It is standard convention to define a new quantity called t to help make the remaining calculations easier. A summary so far of our results using the t quantity is given here, which you can see therefore how we're defining this t quantity and how things can be written in terms of it. We must of course now evaluate this t quantity. The way we'll do this is to partially multiply it out to yield 3 traces, and the third one will be broken up into 2 other traces. Then we'll evaluate all of those separately. So I multiplied it out in 2 steps to keep things clear, and then these 3 terms end up being the 3 traces T1 through T3, where I define them like this specifically, and then that T3 one, of course, I split up, as I said, into 2 smaller traces. Now that the T has been broken up into smaller, more handleable traces, we must compute them. The trace evaluation is the subject of this next section. Now I will be using these identities extensively throughout this trace evaluation, so I just decided to list them at the beginning of the section. So now let's start this trace evaluation by evaluating T1. If we multiply it out completely, we ultimately get this messy result. But of course, terms proportional to products of odd numbers of gamma matrices are 0, because traces of products of odd numbers of gamma matrices are 0. This cuts down on the number of terms significantly. It leaves us with this reduced expression. I then bothered to bring all the factors of the mass together into single prefactors. Then we can simplify things down initially by using this identity here, which gets things cut down quite nicely. to this, and then we can apply this one to simplify them down a little bit more to here. Then we can simplify things down further by using this identity, this one, and this one to produce this result. This identity helps us handle these traces of two gamma matrices. This helps us remove further factors of slashed momentum vectors under the traces, and this helps us zero some things out. Next, we can apply these two identities to simplify things down even further, and we notice there are these two terms that end up canceling that show up as a result of that simplification. We can then use these identities to simplify further, and that simplification ultimately yields two more terms that cancel, and we also arrive at a state where there are traces of products of two gamma matrices showing up again, which we can simplify to dot products by use of that identity, which gets us to here. Then this is an identity similar to ones that I proved in those boxes above at the top of the section, but I only use it once, so I didn't bother to put it in there. I just proved it in the line right where I'm about to use it. Using it to manipulate things quite extensively gets us to here, and we see some simplifications we can do in that with this again. And in this expression we see further opportunities to use this identity to simplify things down, and we can see we're really reducing the trace content extensively by now, but of course we've still got a lot left. Next we can apply these identities to ultimately get it to something that doesn't look any simpler. In fact, it looks longer and more complicated, but actually has further reduced traces, and so it's actually easier to handle. It is still progress. Then we can use this identity and this one to reduce this down further. This identity results in this term vanishing here, and then this one allows us to simplify again terms like this down to dot products. All of that gets us to this simpler, shorter expression, so it's really starting to pay off. Then, given this rather long gamma matrix identity and these two dot products, we can immediately see that these two traces have to be zero, which simplify things down to here. And at this point, there really isn't a convenient way to simplify these down with tricks. We just kind of have to brute force use this identity to evaluate them one by one, which I've done in this table here. Inserting those results back in gets us to this, and then we can combine like terms to ultimately get the final answer for now for T1. Then if we look back at the original traces, we can see that the following momentum interchange, this one here, gives T2 from T1, so performing that on this result for T1 gives us T2 almost for free. We now have the first two traces done. The only one left to calculate is the third trace. Remember from the last section that this had two separate trace terms in it, T3A and T3B, but if we look back at those, we see that this interchange also relates those two to each other, so we actually only have to calculate one of them and then we can get the other one, and I chose to calculate T3A. If we multiply that out, we get an expression like this, which was similar to what we got when we multiplied out T1 originally. And again, we can ignore terms with odd numbers of gamma matrices because they trace to zero. Now, instead of doing a bunch of trickery before ultimately breaking it down and doing these traces individually, I found it easier this time to just do that breakdown earlier. And in this case, I've also organized those individual trace computations in a table. These are the first 6, and on the second page I have the rest of them. This is the 7th one, then the 8th, and then here are the other 10. If we insert all of those results back into T3A, we find this expression here, which is quite long and complicated, but if we combine like terms, we get a much simplified answer, which is just this. We can then use energy conservation to simplify it a little bit further, and we get this final result for T3A. Now we see that it's actually invariant under the momentum interchange that will give us T3B from T3A, so we just have that T3B equals the same thing. So then we can insert those back into T3 and get that, which is just this here. And then we can summarize all of our results. Remember, we defined d sigma in terms of this t quantity, where this t quantity equaled this value in terms of T1, T2, and T3. And now we have these results for T1, T2, and T3. So we're really making some serious progress here. We just need to insert all this back into the scattering cross-section and start simplifying down, select a parameterization, do final simplifications, and then presumably the Bethe-Heitler formula will come out. If we do insert all that back in, we immediately get this. The first thing I did was pull out a factor factor of 8, which gets us to here. Then these two highlighted terms right here can be transferred from the third polarization sum to the first two if all the multiplication and factoring is done correctly, because the prefactors on terms under this sum and under these sums are not the same. Ultimately, that yields these highlighted terms. Now, momentum conservation gives us this value for q squared, and therefore negative q vector squared, which we see showing up right here and right here. So inserting that gives us a nicely reduced expression right there. Then we can transfer the two highlighted terms there to the third polarization sum. And then, of course, we have to keep track of prefactors as we do that again. And ultimately, it duplicates two terms that are under the third polarization sum already. So we just get those factors of 2. We can then factor some things around a little bit in the same area to yield that there, which we then recognize as another example of negative q vector magnitude squared. So inserting that in gives us a further simplified result. We can then transfer these two highlighted terms to the third polarization sum, which gets us to this. With some factoring, we arrive here. Then we can use energy conservation to rewrite these in terms of omega, and then we can factor omega out. That gives us this, and we see something that looks a lot like negative q vector magnitude squared again, but we're missing a factor of 2. But we have one out here, so we can multiply that through, which gets us to this, and then we can substitute in negative q vector magnitude squared again, simplifying it all the way down to this. Then we can do one final term transfer from the first two polarization sums to the third, giving us this. We recognize a perfect square showing up there, which we then write as such. Then we can use momentum conservation to rewrite it like this. Then we remember that k dotted with itself is equal to 0, so we have an expression that finally simplifies down to this. At this point, we have simplified this down as much as we can without selecting the parameterization. So below I have written out the usual parameterization for this problem. For the standard parameterization, we select the outgoing photon to be going in the z direction, the angle theta final to be the angle between the outgoing momentum vector and the z-axis, the angle theta initial to be the angle between the incoming electron momentum vector and the z-axis, and the angle phi to be the angle between the plane containing the z-axis and the incoming electron momentum vector and the plane containing the z-axis and the outgoing electron momentum vector. The parameterization for this reaction is more complicated than for most simple scattering reactions because this reaction can't be fit into a single plane. Based on all of these definitions and some trigonometry, we can work out this parameterization, and with that we can start evaluating various dot products, and we can also use momentum conservation to figure out what q mu must be in terms of that parameterization, and therefore what q squared is, and ultimately what k dot q squared plus omega squared q squared is, which is that term that showed up in this pre-simplified result for the differential scattering cross-section. And with all of these dot product results in terms of the parameterization, we can finish up the simplification. First, we can do the polarization sum, which yields this result, and then we can insert the rest of the parameterization, which immediately gives us this, which we can trivially rearrange into the Bethe-Heitler formula. This is the famous Bethe-Heitler formula finally coming out of all that complicated mathematics. This completes our derivation. So now you know how to derive the Bethe-Heitler formula from quantum electrodynamics. You know the full process, every step, which is really a cool thing because the Bethe-Heitler formula is a beautiful and famous result, and it's really quite a satisfying derivation. If you enjoyed this video, please give it a thumbs up and consider subscribing. D-Trick out.